Welcome back. So, last lecture we have seen robust stability analysis for linear systems and how we saw a glimpse of how one can actually generalize that to nonlinear systems. Here we take a very different approach through this very famous problem called absolute stability problem, or it's called also Luray problem. And Luray problem is essentially treating nonlinear problem as a kind of a midway between linear and nonlinear, and in fact many of the results that we see actually can be specialized to the result that we have seen in the last lecture, but I will not take that approach in terms of trying to show the most general results in absolute stability and things like that. I will show a glimpse of some of the results and things like that, and then come back, see a bunch of examples, and then move on to the more general dissipativity. And if we understand dissipativity, many of these things become relatively straightforward, but if we jump directly into dissipativity, that could be a shock in terms of the level of subtlety involved, right? So we will go through the problem itself, and then we'll look at a couple of conjectures, quite interesting and otherwise historically important. And then we will present these two important criteria called positivity and circle criteria, followed by a very famous criterion called Popov's criterion, right? And the problem itself is quite interesting. It's a way of solving nonlinear problems by dividing the nonlinear part into separate and then linear part into separate. So for the time being, we'll look at this problem as feedback and interconnection of some linear system and a nonlinear system, where the feedback part is a nonlinearity, could be time varying nonlinearity, and it's more or less like your u equals delta times y, right? Otherwise it's identical. It's in that sense it's more general, right? So if I replace this phi, the nonlinearity, with delta, then basically whatever we have seen in the last class will come, right? So what can we assume about this particular nonlinearity? We assume that it's a sector nonlinearity, and I'll show in a picture in a second how that looks like. So if just look at the mathematics, basically if psi is a scalar and m1 and m2 happen to be two numbers that are ordered like this, then we say that psi belongs to the sector m1 m2, and we can show that this inequality is same as basically this two inequalities here, right? So of course, even in the non-scalars in a vector case, basically we still use this terminology of basically psi belong to sector m1 m2, where m1 and m2 now become a kind of a symmetric matrices, where m2 minus m1 is typically non-negative definite. It's not necessary, but that's how it works, right? So let's actually look at this picture in a second, but if d is equal to 0, it's easy to understand this whole thing. We'll essentially simplify, when d is 0, y is simply c of x, and basically when you substitute u into this equation, we end up with x dot equals a times x minus b times this phi of c of x, okay, ignoring the time varying part. That is essentially what we did is we took a nonlinear system, x dot equals f. We put some nonlinearity in separately, and then we put the linear part a and b and things like that. How did we divide these things? And we divided in such a way that the nonlinear part that we left in the problem belongs to some sector m1 m2, and if we know that that happens, then we can address the problem if A satisfies certain conditions. That's the problem of absolute stability problem, right? The absolute stability problem attempts to solve the nonlinear time varying problem through stability conditions involving only a linear system, right? So, but before we go on to anything else, but let me understand this sector nonlinearity, okay? So, ignoring the time varying nature, basically we'll have this phi and y on x and y axis, and sector nonlinearity is essentially, let's say, any nonlinearity that lives in this particular, let's say, sector. In this particular case, I am assuming m1 is the x-axis corresponding to 0, and m2 happens to be infinity, right? Corresponding to y-axis. So if you choose m1 to be 0 and m2 is infinity, I know the difficulty of accepting m2 is infinity for the time being, but let's say if it is possible, then basically that essentially talking about the sector between 0 and 90 degrees, the first and third quadrants, any nonlinearity that is, belongs to this, right? So what is the absolute stability problem? What are the conditions on A, B, C such that the system is stable for all the nonlinearities in this particular sector? So, we may want to solve one single nonlinear system problem, but by actually identifying that there is a particular sector and things like that, we can kind of solve a bigger problem to solve that single problem, but we'll write everything in terms of ABC, right? We'll see in a second how that comes, right? So the absolute stability problem, therefore, the traditional int has become basically we'll have this linear system with a feedback nonlinearity and a set of sector nonlinearities. If we can show somehow stability for the entire sector of nonlinearities, we can show certainly for one of those things, right? So this has been a interesting problem, primarily in Russia and other countries in the Eastern Bloc in those days, and nobody knew in the West in terms of this particular work, but eventually Kalman brought it to the US, as they say. Well, look at this problem. We are trying to solve a robust stability problem, whereas the robustness is with respect to the sector nonlinearities that belong to a particular sector. So one of the questions, therefore, that they had was, how do we solve this, right? And then we will present a couple of conditions and things like that. And then, are they the best conditions? That is the question. And then basically one of the conjectures that came is, okay, instead of looking at all nonlinearities, can we actually just look at only the linearities in this thing? So look at only straight lines, so to speak, any of the straight lines in that sector. If the system is stable with respect to all the linearities, then can we conclude something about nonlinearities, right? So that's Eisenmann's conjecture, and there is an extension to that as Kalman's conjecture. So we will look at all those things in a second, right? So the absolute stability problem is essentially looking at this feedback interconnection of linear system and nonlinear system, where the nonlinearity is sector nonlinearity, it belongs to some sector, and finding stability conditions in ABCD, the linear part, right? So the Eisenmann's conjecture, the conjecture that corresponds to how do we solve this, the solution would perhaps be just looking at all the linearities within that sector, and if that system is stable for the linear part, then perhaps we hope that the nonlinearity problem is solved, right? So that's the Eisenmann's conjecture. And the Kalman came back and said, why? Because Eisenmann conjecture was proven to be wrong. So there is a system that is stable with respect to all linearities in that sector, but it's not necessarily stable for some nonlinearity in that sector, right? Then Kalman came back and said, basically, okay, perhaps it's not true that by just looking at linear linearities within a sector, that may imply actually only certain types of nonlinearities, specifically slope restricted nonlinearities. And eventually it turns out even that is a wrong conjecture. It's a false conjecture, and then a lot of research went into this, and then there are some quite interesting results, and eventually I think there is one result for scalar systems that was shown, but essentially it really never boiled down to anything more than academic curiosity, so we don't try to include that here. But these conjectures, if they were true, it would have allowed us to just treat the entire nonlinear system as a linear system, and then linear robust stability result, and then that would have solved many of the nonlinear problems, okay? But unfortunately, none of these conjectures are true. Ironically, today we look at this absolute stability problem from an exactly opposite angle. We actually, if we solve the nonlinear problem, we know how to solve the linear problem, because static linear uncertainties are actually linearities within this sector nonlinearities, right? So we show absolute stability problem specializes to linear robust stability problem, or gives you a good sufficient condition for robust stability, right? So that brings us to the first result in this particular direction. We will consider the absolute stability problem, that is the feedback interconnection of the linear part and the nonlinear part, where we pick a very specific set of nonlinear sector where m1 is equal to 0, m2 is equal to m, right? Some 0 and m greater than 0. So simply this becomes phi transpose times phi minus m less than equal to 0, right? And it turns out there's a very nice positive real condition. That's how positive real conditions were kind of discovered, and so to speak, but not quite. But anyway, they were discovered independently for a very different reason. But they started looking at conditions on positive realness, using positive realness to solve the absolute stability problem. So anyway, the theorem is something like this. Positivity theorem is if identity plus m times g of s, where m is the positive definite matrix coming from this sector nonlinearity, is strictly positive real, then the zero solution is globally asymptotic stable for all sector nonlinearities that satisfy this inequality, right? We'll look at the proof and then basically go back and discuss, right? Remember, how do we prove this particular theorem? Well, no matter what, eventually this is a nonlinear system, therefore one has to have a linear Lyapunov function and nothing else. So therefore the key connection between your positive realness and then time domain conditions becomes crucial, and then that's where your positive real lemma and things like that become quite useful. So, and we know from the positive real lemma, this I plus mg being strictly positive real if and only if there exists some positive number epsilon and a positive definite matrix such that this linear matrix inequality is satisfied, right? And we can now complete the proof. It's a little bit messy, but otherwise it's a relatively straightforward proof by taking this Lyapunov function x transpose px, and you can show that v dot is going to be not equal to but less than equal to minus epsilon times x transpose px, which will produce strict inequality and guaranteeing asymptotic stability of the feedback interconnection. So I want us to pause a little bit and understand the implication of this, right? So we wanted to solve a nonlinear problem, and we divided that problem into some linear part and nonlinear part, where nonlinear part conveniently belongs to some sector, right? Now I take the linear part and then show that it satisfies some LMI given in front of you, and using your Lyapunov function theory, but the Lyapunov function happens to be the simple quadratic function, and v dot happens to be also quadratic, and we show the nonlinear system is stable. And this is that's why a very powerful result. We've been talking about construction of Lyapunov functions and things like that. In my opinion, this is one of the best ways of constructing Lyapunov functions, is through basically divide the linear part and nonlinear part in such a way that put that into a sector type of nonlinearity and then solve the problem through quadratic Lyapunov functions, right? So let's look at this further. Basically, one can easily show that I plus mg is positive real boils down to a condition in the frequency domain, and that's more or less equivalent to basically the real part of the g in the scalar case is greater than equal to minus 1 over m, and it provides a very graphical condition. You can draw this g of j omega in the complex plane and then look at the real part and how what's the smallest value of that, and then that provides you. So we will look at a illustrative example. So we'll pick this g of s to be some 1 over s times s plus 1 whole square, and the question is basically what's the best sector nonlinearity that this particular system allows, right? I mean, there are two ways of using these results. If you know there is a nonlinearity that belongs to a particular sector, does this g of s satisfies the right I plus mgs condition, or the other way, basically what's the best possible m that we can achieve, right? And we can simply use the scalar result where real part of g is greater than equal to minus 1 over m kind of idea. All we need to basically put s equals j omega and then work on it, and then basically eventually we can see that the real part is going to be something like this, right? And we can see that this particular thing, basically when omega equals 0, it's -2, and then as omega keeps on increasing, this something will happen, and then we can show that it ranges between -2 and 0 perhaps, right? And which simply means the smallest value that this real part can achieve is basically -1/m, and then therefore m is going to be half. And by applying your positivity theorem, we conclude that this system is stable for all sector nonlinearities between 0 and half, right? Just for sake of completion, basically I'm going to write the time domain version. It is a, the denominator of this particular g of s is third order, so therefore the equivalent state space ordinary differential equation will become a third order differential equation. It could be written as actually slightly differently in the state space and things like that. It could be a combination of single order and two or second order systems and things like that. But anyway, this is one simple way of looking at it. If you have this ordinary differential equation involving x triple dot and then x double dot and x dot and a nonlinearity, right? This approach provides an answer saying that this system is stable for all phi between 0 and half, right? And that's a powerful result in my opinion. And we, the LMI provides you actually a Lyapunov function also, right? So, like I said, this is one of the best ways of actually constructing Lyapunov functions. The approach is quite powerful, useful in many nonlinear systems. Is basically divide in such a way that the one part becomes a sector nonlinearity and apply this theory. Okay, so we'll move on to a more generic version of this particular result, where we consider the entire sector M1 and M2 rather than the special case of 0 and M, and one can be proved using the other and things like that, but essentially the result for this particular case, the general case, becomes if I plus m2 times g times inverse of I plus m1 g is strictly positive real, then the zero solution is globally asymptotically stable for all nonlinearities in that particular sector, right? And you can show the proof using your LMI and basically Lyapunov function x transpose px. And that's one way of doing it. And then actually you can show also as a positivity theorem using positivity theorem. Either is fine. If m1 is 0, this is simply you're going to get the standard positivity theorem, that we understand that. And in the scalar case, if m1 and m2 are non-zero, then basically, so if m1 and m2 are non-zero, then basically the frequency domain condition, through positive real, you have to take the real parts and all those things. Basically we'll end up showing that this condition is equivalent to entering or not entering, it can be either of them in the Nyquist plot, right? So that's why it's called circle theorem or circle criterion, and there is an equivalent LMI for that, which I don't state, right? So that is the most general condition for sector nonlinearities, but in reality we can actually even generalize that further and then write in a very generic terms, but it doesn't typically have any nice graphic condition. We will kind of consolidate a lot of these things through dissipativity eventually, so I'm not trying to show all the general results possible within this sector nonlinearities. But there is an interesting extension to some of these results, and one sample, and the most famous one, is called Popov's criterion. There are few others discovered during the time I was doing my dissertation and things like that, but once we understand distributive theory, a lot of these things become relatively straightforward and things like that, so we don't necessarily show all the special cases, right? But what is special about Popov's criterion? First, it applies only to time invariant sector nonlinearities, right? Now that's an important point that for us to understand, is that the circle criterion or the positivity criterion, even if we wanted to just pick say time invariant sector nonlinearities, it doesn't know anything, right? The LMIs are such that basically it will allow time varying nonlinearities. In that sense, it's like a big hammer that the theorem ensures sector nonlinearities that are of time varying nature between those sectors in terms of absolute stability if that condition is satisfied. So there have been a lot of questions, if the sector nonlinearity happens to be time invariant or maybe slope restricted and things like that, if it has some more special features, can we get a better condition? Okay. So Popov was working on that particular problem, and there are even more generalizations, like I said, much into even 1990s and things like that. But the original Popov's result basically goes something like this. If we have this I plus m times I plus ns times g of s is strictly positive real, then the zero solution is globally stable for all the sector nonlinearities between 0 and m. Okay. It's the generalization of the positivity theory, where we essentially require this nonlinearity to be time invariant. It doesn't work if it is time varying, right? So what is the difference? If you actually remember the positivity criterion, basically this n part was 0, right? If this n part is 0, basically that goes back to that one. So if that is true, then the way the result is stated, if there exists a matrix n such that this is true, then basically we have global asymptotic stability. So if positivity criterion is satisfied, then this is trivially satisfied for n equals 0, in which case we will allow even time varying nonlinearities. Your system is such that it's robust enough not just for time invariant sector nonlinearities, but also for time varying, right? But if you do have, say, some other n other than 0 and this is satisfied, this does not imply the other one. So the G may be, more restrictive, that it is not satisfying the positivity criterion, but it satisfies this criterion, but this still allows stability, shows stability for the sector nonlinearities, but of time invariant nature, right? So eventually the questions can come, okay, if we want to allow time invariant nonlinearities, perhaps only linearities, perhaps slope restricted nonlinearities and things like that. So there has been a lot of work in that direction, and you can go on and produce many different results. And then knowing those results is actually quite useful, though in this lecture series we don't get into some of those details. But a lot of these results are kind of can be seen through dissipativity, and then we will look at that in the next chapter. So the proof is actually a direct consequence of the strict positive lemma. So we will have an LMI condition, but of course still we are dealing with nonlinear system, so we need a Lyapunov function, and that's where the beauty of this particular Popov's criterion comes into picture. And note that basically this I plus n times s is itself a transfer function. So in that sense, we actually adding additional dynamics to this. Okay, and how does that work? Well, it turns out basically the Lyapunov function is no longer x transpose px, but actually it involves the nonlinearity itself, and then that's why it's called parameter dependent Lyapunov function, or nonlinearity dependent Lyapunov function, and it's quite a departure from the standard positivity in circle criterion, and that's why it's a celebrated result, and it gives an insight into a beautiful idea that basically you can construct Lyapunov functions through Popov's criterion by not only taking the LMI part, but actually something more that may actually involve the nonlinearity, the part that you're looking at, right? And like I said, there are many extensions to this particular result, and the key idea is to expand your thinking that we don't have to restrict ourselves to positivity and circle criteria through these LMIs, but actually by adding some dynamics within this strict positive real condition, and by getting more generalized Lyapunov functions, right? So that is in a nutshell some glance into absolute stability theory. So once again, we had frequency domain conditions for robust stability, and then we looked at positive real and bounded real lemmas to show how to come back to time domain. Then we saw directly in terms of how Lyapunov functions can be derived for linear unstable systems, but we also saw that all those things could be seen as special case of this very interesting absolute stability theory. Absolute stability theory can be seen as actually a way to address robust stability problem, but in itself it's very powerful because we can actually take a nonlinear system, divide into a linear part and nonlinear part, and the condition is going to be on the linear part, except the more interesting criterion of Popov's criterion, which actually expands on that particular idea to include also some Lyapunov function part that involves nonlinearity. Right? So, and many of these ideas have developed over the years, and then it's actually good to know directly those ideas. But what I'm going to show next is a very general result on feedback interconnections of types of systems called dissipative systems, and then a lot of the sector nonlinearities and the uncertainties that we've been looking at that belong to a certain sets and things like that. Each one of them, every one of them can be shown to be dissipative in a certain sense. And then once we have the general result of feedback interconnections of dissipative systems, then everything that we have seen in these couple of lectures become a special case of that particular result, and much more. And we will look at a few examples where we can use dissipative theory to derive new results and things like that. Thank you.